sklearn Gaussian process. Description: Gaussian processes GPs are a powerful non-parametric Bayesian method for regression and classification. They model the relationship between input features and output values by assuming that the outputs are drawn from a Gaussian distribution whose mean and covariance are determined by the input features and a learned kernel function. GPs are particularly useful for handling complex nonlinear relationships and providing uncertainty estimates in the form of confidence intervals. Inputs X. The input features. Typically a 2D array with each row representing a data point and each column representing a feature. Y. The target values. Typically a 1D array corresponding to the outputs for each input data point. Outputs. YPRED. The predicted output values for new input data points. YSTD. The standard deviation of the predicted output values, representing the uncertainty in the prediction. Steps. Kernel selection: choosing an appropriate kernel function that captures the underlying relationship between input features and output values. Popular choices include the radial basis function RBF kernel, the linear kernel, and the Matron kernel. Kernel hyperparameter optimization: finding the optimal values for the kernel hyperparameters, such as the length, scale, and variance, to best fit the training data. Prediction: using the trained Gaussian process model to predict the output values for new input data points, along with the corresponding uncertainty estimates. Metrics. Mean squared error MSE measures the average squared difference between the predicted values and the actual values. Root mean squared error RMSE, the square root of the MSE, providing a more interpretable measure of prediction error. Log likelihood measures how well the model fits the training data. Visualization plots. Prediction plot visualizes the predicted output values against the actual values, highlighting the confidence intervals. Kernel function plot visualizes the chosen kernel function, showing how it captures the relationship between input features and output values. Fine-tune parameters. Kernel specifies the kernel function to use, e.g., RBF, linear, Matron, alpha regularization parameter that controls the smoothness of the predictions. N restarts optimize a number of random restarts for the optimization algorithm, helping to find the global optimum. Uncertainty methods. Confidence intervals provides a range of values around the predicted output, representing the uncertainty in the prediction. Predictive distribution defines the entire probability distribution of the predicted output, capturing the full uncertainty. Challenges and fixes. Challenge 1: overfitting to the training data, leading to poor generalization performance on unseen data. Sample use case: when the training data is noisy or has a high dimensionality, the model might overfit, resulting in high variance and poor predictions on new data. Fixes. Increase regularization alpha to penalize complex models. Use a more appropriate kernel function that avoids overfitting. Challenge 2: computational complexity for large datasets, making training and prediction time-consuming. Sample use case: when dealing with thousands or millions of data points, training a Gaussian process can be computationally expensive. Fixes. Use approximate inference methods like variational inference or sparse GPs to reduce the computational burden. Leverage parallel processing or GPU acceleration for faster training and prediction. sklearn Gaussian process regressor. Description: the Gaussian process regressor in scikit-learn is a powerful tool for regression tasks. particularly when you need to model complex relationships, capture uncertainties, and perform predictions with confidence intervals. It leverages the concept of Gaussian processes, which are probabilistic models that provide a smooth, continuous function that can capture the underlying trends and patterns within your data. Inputs. X. This is your training data, consisting of a 2D array where each row represents a data point, and each column represents a feature. Y. This is your target variable, a 1D array containing the corresponding values for each data point in X. Outputs. YPRED. This is the predicted value for the target variable based on the fitted Gaussian process model. It's a 1D array representing the predicted output for each input in the test data. YSTD. This is the standard deviation of the predictive distribution at each point in your test data. It provides a measure of uncertainty associated with your predictions. Steps. Data preprocessing. Your data needs to be prepared for Gaussian process regression. This involves scaling your features and potentially handling missing values. Kernel selection. You need to choose a kernel function that defines the covariance between data points. The choice of kernel determines the shape and smoothness of your predicted function. Common kernels include the RBF radial basis function kernel, Matern kernel, and polynomial kernel. Hyperparameter optimization. The kernel often has hyperparameters, e.g., length scale, sigma, that control its behavior. You'll need to optimize these parameters to find the best fit for your data. This can be done through methods like maximum likelihood estimation or cross-validation. Model training. With the kernel and hyperparameters selected, you train the Gaussian process regressor on your training data. Prediction. Once trained, you can use the model to predict values for new input data. The model returns not only the predicted values but also an estimate of the uncertainty in pay. Prediction. Metrics. Mean squared error MSE. This measures the average squared difference between the predicted and actual values. Root mean squared error RMSE. The square root of MSE, representing the average difference in the same units as your target variable. R squared R-score. This indicates the proportion of the variance in the target variable that is explained by your model. Visualization plots. Prediction plot. This visualizes your predictions along with the confidence intervals. It shows how well your model fits the data and how uncertain your predictions are. Kernel function plot. This illustrates the kernel function you chose, showcasing its influence on the smoothness and shape of your predictions. Fine-tune parameters. Kernel. This determines the type of covariance function used to model the relationship between data points. You can explore different kernels to find the best fit for your data. Alpha. This parameter controls the noise level in your model. Higher values of alpha indicate more noise. N restarts optimizer. This parameter influences the optimization process for hyperparameters. It controls the number of times the optimizer restarts from random initial values. Random state. This sets the seed for the random number generator, ensuring reproducibility. Uncertainty methods. Confidence intervals. These provide a range around your predictions, indicating the degree of uncertainty. Standard deviation. This represents the spread of the predictive distribution at each data point, giving a numerical measure of the uncertainty. Challenges and fixes. Challenge 1. Overfitting. If the model learns the training data too well, it might not generalize well to unseen data. Sample use case that resulted in challenge 1. A model with a complex kernel and too many hyperparameters might overfit the training data. Fixes to challenge 1. Simplify the kernel. Consider using a simpler kernel like a linear or RBF kernel, which might prevent overfitting. Regularization: use the alpha parameter to introduce regularization, which helps prevent overfitting by penalizing model complexity. Cross-validation: use cross-validation to assess the model's performance on unseen data and identify overfitting early on. Challenge 2: poor kernel selection. Choosing the wrong kernel can result in poor predictions in a model that doesn't capture the true relationship between your features and target variable. Sample use case that resulted in challenge 2: using a linear kernel for a highly nonlinear relationship might lead to inaccurate predictions. Fixes to challenge 2: experiment with kernels. Try different kernels like RBF, Matern, or polynomial kernels to see which best fits your data. Visualize kernel function. Plot the kernel function to understand its influence on the predictions and identify if it's appropriate for your data. Challenge 3: high computational cost. Gaussian process models can be computationally expensive, especially for large datasets. Sample use case that resulted in challenge 3: training a Gaussian process model with a complex kernel on a large dataset can take significant time. Fixes to challenge 3: sparse Gaussian processes. Explore sparse Gaussian processes, which approximate the full model and can be more efficient for large datasets. Subsampling: if you have a very large dataset, consider subsampling the data to reduce the computational burden. Approximate inference methods like variational inference can be used to approximate the solution, reducing computational cost. sklearn Gaussian process kernels. Description: Gaussian process kernels, also known as covariance functions, are a key component of Gaussian process regression (GPR). They define the relationship between data points, influencing the smoothness and shape of the learned function. These kernels determine how similar two data points are, with higher similarity leading to stronger correlation in the output. They are essential for capturing the underlying structure and dependencies within the data, allowing GPR to make accurate predictions on unseen data. Inputs: X, an array of shape n samples. N features, representing the input data points. Each row corresponds to a data point with its respective features. Y, an array of shape n samples, representing the target values for the input data points. This is used in the fitting process, providing the corresponding outputs for each input data point. Outputs: K, an array of shape n samples. N samples, representing the kernel matrix. This matrix encodes the pairwise similarities between all the data points, reflecting how closely related they are based on the chosen kernel function. Ypred, an array of shape n samples, representing the predicted values for the input data points. These predictions are generated by the Gaussian process regression model based on the learned relationship between the input data and the target values. Steps: define the kernel function. This involves selecting a kernel type that best suits the data's characteristics. Various kernels, like the RBF kernel, are available, each capturing different types of relationships. Compute the kernel matrix. This matrix is calculated by evaluating the kernel function for all pairs of data points. It captures the similarity or correlation between data points. Solve the optimization problem. This step involves finding the optimal model parameters for a kernel function. This is usually done using maximum likelihood estimation or cross-validation. Make predictions once the model is fitted. New predictions can be made for unseen data points using the learned kernel function. Metrics: mean squared error (MSE). This metric measures the average squared difference between the predicted and actual values. Root mean squared error RMSE. This is the square root of the MSE, providing a measure of the prediction error in the same units as the target values. Log likelihood. This metric evaluates the goodness of fit of the model, reflecting how well the model captures the data's underlying structure. Visualization plots. Kernel function plot. This plot visualizes the chosen kernel function, highlighting its behavior and characteristics. It helps understand how the kernel function captures the relationship between data points. Scatter plot of data points and predictions. This plot visualizes the input data points, the predicted values, and their relationship to each other. It provides an intuitive understanding of the model's performance and how well it captures the underlying relationship between the input and output data. Posterior distribution plot. This plot visualizes the uncertainty associated with the predictions. It shows the distribution of possible predictions for each input point, reflecting the confidence in the model's predictions. Fine-tune parameters. Length scale. This parameter controls the smoothness of the learned function. A larger length scale leads to a smoother function, while a smaller length scale results in a more localized function. Noise level. This parameter accounts for measurement noise in the data. A higher noise level indicates more uncertainty in the data, leading to a smoother function with larger confidence intervals. Uncertainty methods. Predictive variance. This method uses the diagonal elements of the inverse kernel matrix to estimate the uncertainty in the predictions. It reflects the spread of the posterior distribution, indicating the confidence in the predictions. Confidence intervals. This method uses the predictive variance to calculate the confidence intervals around the predicted values. These intervals represent the range of likely values for the true output, reflecting the uncertainty in the predictions. Challenges and fixes. Challenge 1. Overfitting. When the model is too complex and captures noise in the data, it can lead to overfitting. This results in poor generalization to unseen data. Sample use case that resulted in challenge 1. A GPR model with a complex kernel function and a large number of parameters may overfit to noisy data, resulting in poor predictions on unseen data. Fixes to challenge 1. Regularization. Introducing regularization techniques, like adding a noise term to the diagonal of the kernel matrix, can help prevent overfitting by penalizing complex models. Cross-validation. Using cross-validation techniques to evaluate the model's performance on unseen data can help identify and avoid overfitting. Simplify the kernel. Choosing a simpler kernel function with fewer parameters can help reduce overfitting by preventing the model from capturing noise. Challenge 2. Poor kernel selection. Choosing a kernel function that does not accurately capture the relationship between the data points can lead to poor model performance. Sample use case that resulted in challenge 2. Using a linear kernel for data with a nonlinear relationship may result in poor predictions, as the linear kernel cannot capture the underlying structure of the data. Fixes to challenge 2. Try different kernels. Experimenting with different kernel functions, such as RBF, polynomial, or Matran, can help identify the best kernel for the given data. Kernel engineering. Combining different kernel functions or customizing kernels to better capture the data's characteristics can improve the model's performance. Feature engineering. Transforming the input features to create more meaningful relationships between data points can help improve the kernel's effectiveness. sklearn Gaussian process kernels. Compound kernel. Description. The compound kernel class in scikit-learn's Gaussian process library allows you to combine multiple kernels into a single kernel. representing a more complex relationship between input features and the target variable. This is particularly useful when modeling data with multiple sources of variability or when different kernel types are suitable for different aspects of the data. Inputs. Kernel objects. Compound kernel takes one or more instances of kernel objects as input. These kernel objects represent different aspects of the relationship you want to model between the input features and the target variable. You can use different types of kernels like RBF, linear, constant, and others. Kernel weights optional if you want to assign different weights to the individual kernels in the combination. You can provide these weights as input. This allows you to adjust the influence of each kernel on the final model. Outputs. Combined kernel object. The compound kernel class returns a single kernel object that represents the combined effect of all input kernels. You can use this combined kernel object in your Gaussian process model to make predictions. Kernel weights optional if you provided weights as input. The compound kernel class also returns the weights that were applied to each individual kernel. Steps. Kernel initialization. You initialize the compound kernel object by passing the kernel objects you want to combine. You can optionally provide weights for each kernel as well. Kernel combination. Internally, the compound kernel object combines the input kernels according to the specified weights. It effectively creates a single kernel function that captures the combined effect of all input kernels. Model fitting. You can then use the combined kernel object in a Gaussian process regression or classification model. The model will fit the data using the combined kernel to learn the relationship between the input features and the target variable. Metrics. Mean squared error MSE. This metric measures the average squared difference between the model's predictions and the actual target values. It is commonly used to evaluate the performance of regression models. Log loss cross entropy. This metric is used for evaluating the performance of classification models. It measures the difference between the predicted probability distribution and the actual distribution of classes. R squared measures how much of the variance in the target variable is explained by the model. It ranges from 0 to 1, with higher values indicating a better fit. Visualization plots. Kernel function visualization. You can plot the combined kernel function to visualize its behavior and gain insights into the relationships it models. Prediction interval plots plot the predicted values with confidence intervals to visualize the uncertainty in the model's predictions. This can be helpful for understanding the reliability of the model's predictions. Fine-tune parameters. Kernel weights. You can adjust the weights of individual kernels in the compound kernel to fine-tune the model's behavior. Experiment with different weights to find the best balance between the different kernel contributions. Kernel parameters. Each individual kernel might have its own parameters, e.g., length scale for RBF kernel. You can tune these parameters to optimize the model's performance. Uncertainty methods. Bayesian prediction intervals. The Gaussian process framework provides a natural way to compute prediction intervals, which quantify the uncertainty in the model's predictions. Monte Carlo dropout. This technique can be used to estimate uncertainty in deep learning models. You can apply Monte Carlo dropout during inference to generate multiple predictions and use them to calculate uncertainty estimates. Challenges and fixes. Challenge 1. Overfitting to the training data. If the compound kernel is too complex or has too many parameters, the model may overfit to the training data, leading to poor performance on unseen data. Sample use case that resulted in challenge 1. A model with a complex compound kernel containing Many different kernel components and a large number of parameters was trained on a small dataset. The model was able to achieve very low error on the training data but performed poorly on the test. Data fixes to challenge 1. Use cross-validation. Divide the data into multiple folds and train the model on different combinations of these folds. This helps to prevent overfitting by evaluating the model's performance on unseen data. Regularization. Apply regularization techniques, such as L1 or L2 regularization, to penalize large model parameters, which helps to prevent overfitting. Simplify the kernel. Reduce the complexity of the compound kernel by using fewer kernel components or simpler kernel types. Challenge 2. Choosing the right kernel combination. Selecting the appropriate kernels and weights for the compound kernel can be challenging. A poorly chosen kernel combination can lead to a model that does not capture the true relationship between the input features and the target variable. Sample use case that resulted in challenge 2. A model was trained using a compound kernel that included a linear kernel and a periodic kernel, but the data did not exhibit a clear linear or periodic relationship. This resulted in a poor model fit. Fixes to challenge 2. Domain knowledge. Use domain knowledge to guide the choice of kernels. Consider the characteristics of the data and the underlying relationships you expect to model. Feature engineering. Transform the input features to make them more suitable for specific kernel types. For example, you could apply a logarithmic transformation to features that exhibit exponential growth. Feature selection. Select the most relevant features for the model. This can simplify the task of choosing an appropriate kernel combination. Challenge 3. Computational complexity. Combining multiple kernels can lead to a more complex model with higher computational costs, especially for large datasets. Sample use case that resulted in challenge 3. A compound kernel with several kernel components was used to model a large dataset with millions of data points. The model training process was extremely slow due to the high computational complexity. Fixes to challenge 3. Kernel approximation techniques. Use techniques like random Fourier features or Nystrom approximation to reduce the computational cost of evaluating the kernel function. Sparse kernel methods. Employ sparse kernel methods, such as the sparse greedy matrix approximation, to reduce the number of kernel evaluations required. Optimization techniques. Use efficient optimization algorithms, such as stochastic gradient descent (SGD), to speed up the model training process. sklearn Gaussian process kernels. Constant kernel description. The constant kernel represents a constant function in the Gaussian process GP model. It is a simple kernel that assumes the target function is approximately constant, leading to a flat prior over the function space. This kernel is often used in combination with other kernels to account for global bias or scaling. In the data inputs, XA2D array representing the input data points. Each row corresponds to a data point, and each column corresponds to a feature. YA1D array representing the target values corresponding to the input data points. Outputs, KA2D array representing the kernel matrix. The element at position I, J in the matrix represents the similarity between the ITH and JTH data points. Steps. The constant kernel takes the input data X and calculates the similarity between each pair of data points. The kernel matrix K is then calculated using the formula key J constant value. Metrics. R squared measures the proportion of the variance in the target values that is explained by P model. Mean squared error MSE measures the average squared difference between the predicted values and the actual values. Visualization plots. Scatter plot of the input data points colored by their target values. Heat map of the kernel matrix showing the similarity between data points. Fine-tune parameters. Constant value, a scalar value representing the constant value of the kernel. This parameter determines the overall scale of the kernel function. Uncertainty methods. Bayesian confidence intervals provides a measure of uncertainty in the predicted values based on the posterior distribution of the GP model. Predictive variance measures the variance of the predicted values at each input point. Challenges and fixes. Challenge 1: overfitting. If the constant value is too high, the model may overfit the data, leading to poor generalization performance. Sample use case that resulted in challenge 1: using a high constant value for a dataset with a strong underlying trend. Fixes to challenge 1: reduce the constant value or combine the constant kernel with other kernels to model the trend. Challenge 2: underfitting. If the constant value is too low, the model may underfit the data, failing to capture the global bias in the target function. Sample use case that resulted in challenge 2: using a low constant value for a dataset with a strong global bias. Fixes to challenge 2: increase the constant value or combine the constant kernel with other kernels to account for the global bias. sklearn Gaussian process kernels. Product description. Explain in detail the dot product kernel, also known as the linear kernel, computes the dot product between two input vectors. It assumes a linear relationship between the input features and the target variable. This kernel is suitable for data that exhibits linear trends. Inputs. Input 1: explain in detail x1, the first input vector, a 1D array of shape n samples 1. Input 2: explain in detail x2, the second input vector, a 1D array of shape n samples 2. Output 1: explain in detail k, the kernel matrix of shape n samples 1. N samples 2, where key j represents the dot product between x1i and x2j. Output 2: explain in detail none. Steps. Step 1: explain in detail. The kernel calculates the dot product between the corresponding elements of the input vectors x1 and x2. Step 2: explain in detail. The resulting values are stored in the kernel matrix K. Metrics. Metric 1: explain in detail. R² score. R measures the goodness of fit of the model, indicating the proportion of variance in the target variable explained by the model. Metric 2: explain in detail. Mean squared error MSE measures the average squared difference between the predicted values and the actual values. Visualization plots. Visualization plot 1: explain in detail. Scatter plots can be used to visualize the linear relationship between input features and the target variable. Visualization plot 2: explain in detail. Contour plots can be used to visualize the decision boundary of the model, highlighting areas of high and low predicted values. Parameter 1: explain in detail none. Parameter 2: explain in detail none. Uncertainty method 1: explain in detail. The model provides uncertainty estimates through pay variance of the predicted values. Uncertainty method 2: explain in detail. Confidence intervals can be constructed around the predicted values to quantify the uncertainty. Challenge 1: explain in detail. The dot product kernel can be sensitive to the scaling of the input features. If the features are on vastly different scales, the kernel can be dominated by the feature with the largest scale. Sample use case that resulted in challenge 1: if one feature has values in the range 0 to 1 and another feature has values in the range 1000 to 2000, the kernel will be dominated by the second feature. Fixes to challenge 1 feature scaling techniques, such as standardization or normalization, can be applied to bring the features to a common scale. Challenge 2. Explain in detail the dot product kernel can struggle to capture nonlinear relationships in the data. Sample use case that resulted in challenge 2. If the data exhibits a nonlinear relationship between the input features and the target variable, the dot product kernel may not be able to model it accurately. Fixes to challenge 2 nonlinear kernels, such as the RBF kernel or the polynomial kernel, can be used to capture nonlinear relationships in the data. sklearn Gaussian process kernels exp sin squared. Description: the exp sin squared kernel is a stationary kernel that is suitable for modeling data with periodic patterns. It combines a periodic component, represented by a sine function, with an exponential decay component, resulting in a kernel that oscillates with a period of length period and decays with a characteristic length scale of length scale. The kernel is defined as kx1, x2, xp, x1, x22 to length scale 2 sin 2 pi x1, x2 period 2, where x1 and x2 are 2 input points. Length scale is the length scale of the exponential decay, and period is the period of the sine function. Inputs: x1 the first input point, a one-dimensional array or scalar. x2 the second input point, a one-dimensional array or scalar. Outputs: k the kernel value between the 2 input points, a scalar. Steps: calculate the squared distance between the 2 input points x1 x22. Divide the squared distance by twice the squared length scale x1 x22 to length scale 2. Take the exponential of the result, express x1 x22 to length scale 2. Calculate the sine of twice pi times the difference between the input points divided by pi. Period sin 2 pi x1 x2 period. Square the sine value sin 2 pi x1 x2 period 2. Multiply the exponential value and the squared sine value to obtain the kernel value, express x1 x22. 2 length scale 2 sin 2 pi x1 x2 period 2. Metrics: the exp sin squared kernel does not directly provide metrics, but it can be used in conjunction with a Gaussian process to estimate the underlying function and its uncertainty. Metrics such as mean squared error MSE or root mean squared error RMSE can be used to evaluate the model's performance on a test set. Visualization plots: the kernel function can be visualized by plotting its value for different pairs of input points. This can help to understand the shape of the kernel and how it captures the periodic nature of the data. The Gaussian process itself can be visualized by plotting its predicted mean and variance for different input points. This can provide insights into the model's uncertainty and how it interpolates between observed data points. Fine-tune parameters. Length scale controls the length scale of the exponential decay. A larger length scale corresponds to a slower decay, meaning that the kernel will be more correlated for points that are further apart. Period controls the period of the sine function. A larger period corresponds to a longer wavelength. Uncertainty methods. The exp sin squared kernel can be used in conjunction with the Gaussian process to estimate the uncertainty of the predicted function. The Gaussian process provides a distribution over possible functions that are consistent with the observed data, and the uncertainty is captured by the variance of this distribution. Challenges and fixes. Challenge 1: overfitting to the data. Sample use case that resulted in challenge 1: if the length scale and period parameters are not chosen appropriately, the model may overfit to the training data and fail to generalize well to new data. Fixes to challenge 1. Use cross-validation to tune the hyperparameters of the kernel. Consider using a regularization term in the Gaussian process to penalize complex models and prevent overfitting. Challenge 2. Choosing the appropriate period. Sample use case that resulted in challenge 2 if the period of the sine function is not correctly chosen. The model may not capture the periodicity in the data. Fixes to challenge 2. Perform a Fourier analysis of the data to estimate the dominant frequency and use that as the period. Explore different values of the period and select the one that leads to the best model. Performance. Sklearn Gaussian process kernels exponentiation. Description. Kernel: the kernel to be exponentiated. This could be any of the kernels provided by scikit-learn, such as the RBF kernel, the Matern kernel, or the rational quadratic kernel. Exponent: the exponent to which the kernel is raised. This value should be a positive number. Exponentiated kernel: the kernel after being raised to the specified exponent. Modified kernel output: the output of the kernel is modified based on the exponent. This modification can affect the smoothness and the scale of the output. The kernel is raised to the specified exponent element-wise. This means that each element of the kernel matrix is raised to the power of the exponent. The exponentiated kernel is then used in the Gaussian process regression or classification model. Kernel smoothness: the smoothness of the kernel can be measured by its differentiability. Higher exponents result in smoother kernels. Kernel scale: the scale of the kernel can be measured by its variance. Higher exponents result in kernels with larger variances. Kernel function: plot the kernel function for different values of the exponent. This will show how the exponent affects the shape of the kernel. Mean function: plot the mean function of the Gaussian process for different values of a exponent. This will show how the exponent affects the smoothness of the predictions. Exponent: adjust the exponent to control the smoothness and scale of the kernel. A higher exponent results in a smoother kernel with a larger variance. Marginal variance: the marginal variance of the Gaussian process is a measure of the uncertainty of the predictions. The marginal variance is directly proportional to the kernel's variance. Confidence intervals: the confidence intervals of the Gaussian process predictions can be calculated using the marginal variance. The width of the confidence intervals is proportional to the marginal variance. Overfitting: if the exponent is too high, the kernel can become too smooth and overfit the data. This can lead to poor generalization performance. Sample use case that resulted in challenge 1: training a Gaussian process regression model with a very high exponent on a noisy dataset. Reduce the exponent to a lower value. Underfitting: if the exponent is too low, the kernel can become too rough and underfit the data. This can lead to poor predictions, especially in regions where there is little data. Sample use case that resulted in challenge 2: training a Gaussian process classification model with a very low exponent on a dataset with complex decision boundaries. Fixes to challenge 2: increase the exponent to a higher value. Sklearn Gaussian process kernels hyperparameter. Description: explain in detail. Inputs: a set of training data points, represented as an array of shape n samples. N features, where n samples is the number of samples and n features is the number of features. The corresponding target values for each training data point, represented as an array of shape n samples. A trained Gaussian process model that can be used to predict the target values for new data points. The predicted target values for new data points. Steps: the Gaussian process model is trained using the training data and target values. This involves estimating the hyperparameters of the kernel function. The trained model is then used to predict the target values for new data points. This involves computing the covariance between the new data points and the training data points, and then using this covariance to make predictions. Metrics. Mean squared error (MSE) measures the average squared difference between the predicted and actual target values. Root mean squared error (RMSE) the square root of the MSE. R squared R measures the proportion of the variance in the target values that is explained by the model. Visualization plots. Scatter plot of the predicted target values versus the actual target values. Plot of the predicted target values with confidence intervals. The length scale parameter controls the smoothness of the kernel function. A smaller length scale results in a more wiggly function, while a larger length scale results in a smoother function. The signal variance parameter controls the amplitude of the kernel function. A larger signal variance results in a larger amplitude, while a smaller signal variance results in a smaller amplitude. Confidence intervals. These intervals provide a measure of the uncertainty in the predictions made by the model. Predictive distributions. These distributions provide a more complete picture of the uncertainty in the predictions, as they include information about the shape of the distribution as well as the confidence intervals. Challenge 1. Overfitting. The model may overfit to the training data, resulting in poor performance on unseen data. Sample use case that resulted in Challenge 1: training a Gaussian process model with a very small length scale on a dataset with a lot of noise. Fixes to Challenge 1: use cross-validation to evaluate the performance of the model on unseen data. Regularize the model by adding a small amount of noise to the diagonal of the covariance matrix. Use a different kernel function, such as the RBF kernel, which is less prone to overfitting. Challenge 2: computational complexity. The computational complexity of Gaussian process models can be high, especially for large datasets. Sample use case that resulted in Challenge 2: training a Gaussian process model on a dataset with millions of samples. Fixes to Challenge 2: use a sparse Gaussian process model, which only considers a subset of the training data points. Use approximate inference techniques, such as variational inference or expectation propagation. sklearn Gaussian process kernels. Kernel description. The kernel class in scikit-learn's Gaussian process module represents a mathematical function that describes the similarity between two data points. It's a fundamental component of Gaussian process regression (GPR), which uses the kernel to model the relationships between input data and target values. Kernels allow GPR to learn complex nonlinear functions, capturing patterns and dependencies in the data. Inputs. X. This is the input data, usually a 2D NumPy array where each row represents a data point, and each column represents a feature. Y. This is the target data, typically a 1D NumPy array representing the corresponding outputs for each input data point. Outputs. Kernel matrix K. The kernel function computes the similarity between all pairs of input data points and outputs a square matrix K where each element key J represents the similarity between data points I and J. Predicted output YPRED. The kernel matrix is used to perform predictions for new input data points. GPR uses the kernel to determine the relationship between the input data and the target data, and then uses this relationship to predict the output for new input data. Steps. Define kernel. Choose a suitable kernel function, e.g. RBF, linear, polynomial that aligns with the expected relationships in your data. Fit kernel. The chosen kernel is fitted to the provided training data X, Y, This involves learning the hyperparameters of the kernel, which control its shape and smoothness. Predict given new input data points. The kernel calculates the similarity to the training data using the learned kernel function. This information is used to predict the corresponding output values. Metrics. Mean squared error MSE measures the average squared difference between the predicted and actual target values. Lower MSE indicates a better fit. Root mean squared error RMSE the square root of MSE, providing a more interpretable measure of prediction error. R squared indicates the proportion of variance in the target variable that is explained by the model. A higher R squared value suggests a better model fit. Visualization plots. Kernel function plot visualizes the kernel function itself, revealing the shape and behavior of the similarity function. Predicted vs actual plot shows the predicted output values against the actual target values, providing an assessment of the model's accuracy. Fine-tune parameters. Length scale L controls the smoothness of the kernel. Smaller values indicate more localized relationships, while larger values suggest broader influences. Variance sigma 2 scales the kernel function, adjusting the overall magnitude of the similarity values. Noise level sigma 2 represents the level of noise assumed in the data, influencing the smoothness of the prediction. Uncertainty methods. Confidence intervals provides a range of plausible values for the prediction, reflecting the model's uncertainty about its output. Predictive variance quantifies the uncertainty of the predictions, highlighting areas where the model is less confident. Challenges and fixes. Challenge 1. Overfitting. If the kernel is too complex, e.g., high-length scale and the data is limited, the model may overfit the training data, resulting in poor performance on unseen data. Sample use case that resulted in challenge 1 using an RBF kernel with a very large length scale on a small dataset of only 10 data points could lead to overfitting. Fixes to challenge 1. Regularization. Introduce regularization techniques, e.g., L2 regularization to penalize overly complex kernels, preventing overfitting. Cross-validation. Use cross-validation techniques to evaluate the model's performance on unseen data and choose the appropriate kernel complexity. Challenge 2. Computational cost. Calculating the kernel matrix for large datasets can be computationally expensive. Sample use case that resulted in challenge 2. Training a GPR model with a large dataset, e.g., millions of data points using a complex kernel, e.g., RBF, can lead to high computational cost. Fixes to challenge 2. Approximations. Employ approximate methods like Nystrom approximation or sparse Gaussian processes to reduce the computational complexity. Kernel approximation. Use faster to compute kernels like the linear kernel or polynomial kernels. When possible, hardware acceleration. Utilize GPUs or specialized hardware for accelerating matrix computations. Sklearn Gaussian process kernels. Matern. Description. The Matern kernel is a stationary kernel that is commonly used in Gaussian process GP regression for modeling smooth functions. It provides a balance between smoothness and flexibility, making it suitable for a wide range of applications. The Matern kernel's smoothness is controlled by a parameter called mu, which dictates the number of derivatives that are continuous. Inputs. X, an array of shape n samples. N features representing the input data points. Each row corresponds to a sample, and each column represents a feature. Y, an array of shape n samples, or n samples. N targets representing the target values corresponding to the input data points. Outputs. A covariance matrix of shape n samples. N samples. representing the pairwise covariances between the input data points. A predicted output value for a new input data point, along with the associated uncertainty variance. Steps. Calculate the distance between input data points. The kernel function is based on the distance between input data points. The distance can be calculated using various metrics, such as Euclidean distance, Manhattan distance, or other distance metrics appropriate for the specific application. Apply the Matern kernel function. The Matern kernel function is then applied to the calculated distances to determine the covariance between the input data points. The function involves a combination of exponential and Bessel functions. Compute the covariance matrix. The pairwise covariances between all input data points are calculated and stored in a covariance matrix. This matrix is used in GP regression to infer the relationships between the data points. Metrics. Log likelihood measures the goodness of fit of the GP model to the data. Higher values indicate a better fit. Mean squared error MSE measures the average squared difference between the predicted and actual target values. Lower values indicate better prediction accuracy. Visualization plots. Kernel function visualization. Plotting the Matern kernel function with varying distance values and new parameters can help understand the effect of these parameters on the smoothness of a kernel. Predicted function visualization. Plotting the predicted function along with the confidence intervals based on the uncertainty can visualize the GP model's predictions and the associated uncertainty. Fine-tune parameters. Nu. This parameter controls the smoothness of the kernel. Higher values of nu lead to smoother functions. Common values for nu include 1.5, 2.5, and 52. Length scale. This parameter determines the characteristic length scale of the function. Larger values indicate smoother functions that vary slowly. Uncertainty methods. Marginal variance provides a measure of the uncertainty in the predicted value at a given input data point. Confidence intervals constructs a range around the predicted value, representing the interval within which the true value is likely to fall with a certain probability. Challenges and fixes. Challenge 1. Overfitting. When the model is too complex, it can fit the training data too closely and fail to generalize well to unseen data. Sample use case that resulted in challenge 1. A GP model with a high nu value and a small length scale is used to fit a noisy dataset. Fixes to challenge 1. Regularization. Introduce a penalty term in the model's objective function to discourage overly complex models. Cross-validation. Split the data into training and validation sets. Train the model on the training set and evaluate its performance on the validation set. Challenge 2. Poor performance on data with complex dependencies. The Matern kernel may struggle to capture highly nonlinear relationships in the data. Sample use case that resulted in challenge 2. Using a Matern kernel to model a dataset with strong periodic patterns. Fixes to challenge 2. Use a different kernel. Consider using a more flexible kernel, such as the rational quadratic kernel or a custom kernel designed for the specific data. Characteristics. Feature engineering. Transform the input features to capture the underlying dependencies in a data. Multi-output GP. Utilize a multi-output GP model to capture the complex relationships between multiple output variables. sklearn, Gaussian process, kernels, pairwise kernel. Description. The pairwise kernel is a versatile kernel that allows for the construction of custom Gaussian process kernels based on a user-defined function that measures the similarity between pairs of data points. This function provides a great deal of flexibility for modeling diverse relationships between data points and capturing complex patterns. Inputs. Metric: a function that takes two data points as input and returns a scalar value representing their similarity. This metric can be any function that returns a scalar value, allowing for customization based on the specific application and data characteristics. Quarks: additional keyword arguments that are passed to the metric function. This allows for further customization of the metric based on the specific requirements of a problem. Outputs. Kernel function returns a kernel function that can be used in a Gaussian process model. This kernel function encapsulates the similarity information captured by the metric, allowing the Gaussian process to learn and predict based on the relationships between data points. Quarks: the same keyword arguments passed to the metric function, which are passed along to the generated kernel function for consistency. Steps. The pairwise kernel takes as input a metric function that defines the similarity between pairs of data points. This metric function can be any function that returns a scalar value. The pairwise kernel constructs a kernel function that calculates the similarity between all pairs of data points using the provided metric function. This similarity information is then used by the Gaussian process model to learn and make predictions. Metrics. The choice of metric is crucial for the performance of the pairwise kernel. Different metrics can capture different aspects of similarity between data points, leading to different kernel functions and ultimately different model predictions. Visualization plots. By visualizing the kernel function, one can gain insights into how the chosen metric captures the relationships between data points. Fine-tune parameters. The pairwise kernel itself does not have any tunable parameters. However, the choice of metric and the corresponding quarks passed to the metric function allow for fine-tuning the kernel based on the specific problem. Uncertainty methods. The pairwise kernel does not directly influence the uncertainty estimation in a Gaussian process model. Uncertainty estimation is handled by the Gaussian process model itself. Challenges and fixes. Challenge 1: choosing the appropriate metric function for a given problem can be challenging, as different metrics capture different aspects of similarity. Sample use case that resulted in challenge 1 in a problem involving image data. Using a Euclidean distance metric might not capture the similarity between images well, as it doesn't consider the spatial relationships between pixels. Fixes to challenge 1. Explore different similarity metrics, such as cosine similarity or a custom metric tailored to the specific image features, which could potentially capture the relationships between images more effectively. Experiment with different metric functions and evaluate the performance of the resulting kernel in the context of the specific problem. Challenge 2: handling large datasets can be computationally expensive, as the pairwise kernel needs to calculate the similarity between all pairs of data points. Sample use case that resulted in challenge 2: processing a large dataset of images might require a significant amount of computational time for the pairwise kernel to compute the similarity between all pairs. Fixes to challenge 2. Use efficient data structures and algorithms to compute the similarity between data points. Consider using approximation techniques, such as Nystrom approximation, to reduce the computational complexity of calculating the kernel matrix. Explore dimensionality reduction techniques to reduce the number of data points before applying the pairwise kernel. sklearn Gaussian process kernels product. Description: the product kernel in scikit-learn's Gaussian process framework combines multiple kernels to create a more complex kernel function. This allows for modeling complex relationships in the data that might not be captured by a single kernel. Inputs. Input 1 kernels. The product kernel takes a list of 2 or more kernel objects as input. Each kernel represents a different aspect of the relationship between the input features and the output values. Input 2 data. The product kernel requires training data, consisting of input features and corresponding output values. Outputs. Output 1 kernel matrix. The product kernel calculates a kernel matrix that represents the similarity between all pairs of data points. Output 2 prediction function. The kernel matrix is used to construct the prediction function that can be used to make predictions for new data points. Steps. Step 1. Calculate individual kernel matrices. For each input kernel, the kernel matrix is computed using the provided data. Step 2. Multiply kernel matrices. The individual kernel matrices are element-wise multiplied to create the final kernel matrix for the product kernel. Metrics. Metric 1. Negative log marginal likelihood (NLML) measures the goodness of fit of the Gaussian process model. Lower values indicate a better fit. Metric 2. Root mean squared error (RMSE) measures the average error between the model's predictions and the actual values. Visualization plots. Visualization plot 1 kernel matrix heat map visualizes the kernel matrix as a heat map, showing the similarity between data points. Visualization plot 2 prediction function plot plots the predicted values against the actual values, showing the model's performance. Fine-tune parameters. Parameter 1 kernel parameters. The individual kernels often have parameters that need to be tuned. Parameter 2 noise level controls the amount of noise in the model. Uncertainty methods. Uncertainty method 1 predictive variance calculates the variance of the predictions, providing a measure of uncertainty. Uncertainty method 2 confidence intervals constructs confidence intervals around the predictions, providing a range of possible values. Challenges and fixes. Challenge 1 overfitting. The product kernel can overfit the data, especially when using many kernels or complex kernels. Sample use case that resulted in challenge 1 using a product of multiple radial basis function (RBF) kernels with different length scales, leading to a highly flexible model that fits the training data well but fails to generalize to unseen data. Fixes to challenge 1. Use regularization. Add a noise term to the kernel function to prevent overfitting. Cross-validation. Use cross-validation techniques to select the best kernel and hyperparameters. Feature selection. Select relevant features and avoid using irrelevant features to prevent overfitting. Challenge 2 computational complexity. Calculating the kernel matrix for large datasets can be computationally expensive, especially for complex kernels. Sample use case that resulted in challenge 2 using a product kernel with several kernels in a large dataset, leading to a long training time. Fixes to challenge 2. Use approximate methods. Use approximations such as Nystrom approximation or random Fourier features to speed up kernel matrix computation. Subsample data. Use a subset of the data for training and then make predictions on the full dataset. Optimize kernel selection. Choose kernels that are computationally efficient for the given data. Sklearn Gaussian process kernels (RBF). Description. Explain in detail the radial basis function (RBF) kernel, also known as the Gaussian kernel, is a widely used kernel in Gaussian process GP regression. It's a stationary kernel that measures the similarity between two data points based on the Euclidean distance between them. The RBF kernel assumes that data points that are closer in the feature space are more likely to have similar target values. Inputs. Input 1 explain in detail x1 the first data point, represented as a vector of features. Input 2 explain in detail x2 the second data point, represented as a vector of features. Outputs. Output 1 explain in detail a scalar value representing the similarity between the two data points, based on the Euclidean distance between them. Output 2 explain in detail a covariance matrix if applied to a set of data points. Steps. Step 1 explain in detail the kernel function computes the Euclidean distance between x1 and x2. Step 2 explain in detail it then applies a Gaussian function to this distance. The Gaussian function is defined by a length scale parameter gamma, which determines the width of the Gaussian bell curve. Metrics. Metric 1 explain in detail mean squared error MSE measures the average squared difference between the predicted values and the actual values. Metric 2 explain in detail root mean squared error RMSE represents the square root of a average squared error. Visualization plots. Visualization plot 1 explain in detail scatter plot with a heat map representing the kernel values for a set of data points, showing how the similarity changes with the distance between them. Visualization plot 2 explain in detail contour plot visualizing the kernel values across different distances, highlighting the Gaussian function behavior. Fine-tune parameters. Parameter 1 explain in detail length scale gamma. The length scale parameter controls the width of the Gaussian bell curve. A larger length scale results in a wider curve, implying that points further apart can still be considered similar. A smaller length scale results in a narrower curve, meaning that only points very close to each other are considered similar. Parameter 2 explain in detail constant value, an optional constant value added to the kernel. It can be used to introduce a bias term into the GP model. Uncertainty methods. Uncertainty method 1 explain in detail predictive variance. The GP model provides an estimate of the uncertainty in its predictions based on the training data and the kernel function. This uncertainty is represented by the predictive variance, which is higher for regions where there is less training data. Uncertainty method 2 explain in detail confidence intervals. Confidence intervals are constructed based on the predictive variance to indicate the range within which the true value is expected to lie with a certain probability. Challenges and fixes. Challenge 1 explain in detail overfitting to the training data. If the length scale parameter is too small, the kernel function may overfit to the training data, resulting in poor generalization to unseen data. Sample use case that resulted in challenge 1. A GP model with a small length scale parameter might predict very high values for points close to training data and very low values for points far away, even if the true relationship is smoother. Fixes to challenge 1: increase the length scale parameter or use cross-validation to find an optimal value. Challenge 2: explain in detail underfitting the training data. If the length scale parameter is too large, the kernel function may underfit the training data, failing to capture the underlying relationships. Sample use case that resulted in challenge 2: a GP model with a large length scale parameter might produce predictions that are too smooth and fail to capture the variations in the data. Fixes to challenge 2: decrease the length scale parameter or explore alternative kernels like a Matran kernel. sklearn Gaussian process kernel's rational quadratic. Description: the rational quadratic kernel is a stationary kernel that combines multiple squared exponential kernels with different length scales. It is a generalization of the squared exponential kernel and allows for more flexibility in modeling data with varying degrees of smoothness. Inputs: X the input data, typically a 2D array of shape n samples. N features. Y the output data, typically a 1D array of shape n samples. K the kernel matrix, a 2D array of shape n samples. N samples containing the kernel values between all pairs of input data points. Steps: compute the squared Euclidean distance between all pairs of input data points. Apply the rational quadratic kernel function to the distances. Metrics: mean squared error MSE measures the average squared difference between the predicted and actual values. R squared measures the proportion of variance in the output data that is explained by the model. Visualization plots: kernel matrix plot visualizes the kernel values between all pairs of input data points. Predicted vs. actual values plot compares the predicted output values with the actual output values. Length scale: the length scale parameter controls the smoothness of the kernel function. A larger length scale indicates a smoother function, while a smaller length scale indicates a more wiggly function. Alpha: the alpha parameter controls the relative weighing of the different squared exponential kernels that are combined. A larger alpha value gives more weight to kernels with larger length scales. Predictive variance provides a measure of the uncertainty in the predicted output values. Confidence intervals defines a range of values within which the true output values are likely to fall. Challenge 1: overfitting to the training data. Sample use case that resulted in challenge 1 using a too complex kernel with many parameters can lead to overfitting, resulting in a model that performs well on the training data but poorly on unseen data. Fixes to challenge 1: use regularization techniques to prevent overfitting. Use cross-validation to select the optimal model complexity. Challenge 2: choosing appropriate kernel parameters. Sample use case that resulted in challenge 2: the performance of the model depends heavily on the choice of kernel parameters, such as the length scale and alpha. Fixes to challenge 2: use grid search or Bayesian optimization to find the optimal kernel parameters. Use domain knowledge to guide the choice of kernel parameters. sklearn Gaussian process kernels sum. Description: the sum kernel in scikit-learn's Gaussian process framework is a powerful tool for combining multiple kernels into a single, more complex kernel. This allows you to model a wider range of relationships within your data. Essentially, the sum kernel calculates the sum of the output of each individual kernel it encompasses. This can be useful for capturing different aspects of your data, such as both short-range and long-range correlations. Inputs: Input 1 kernel 1. This is a scikit-learn kernel object, such as the RBF kernel, the linear kernel, or even another composite kernel. The first kernel in the sum. Input 2 kernel 2 optional. This is another scikit-learn kernel object. You can add as many kernels as you need for your model. The second kernel in the sum. Outputs: Output 1 the sum kernel. This is a combined kernel object that represents the sum of the individual kernels. The resultant combined kernel. Output 2 covariance matrix. The sum kernel, when applied to data, generates a covariance matrix that reflects the combined effects of the individual kernels. The matrix representing the covariances between points, as calculated by the combined kernel. Steps: Step 1. Initialize the sum kernel. Create an instance of the sum kernel by passing the individual kernels as arguments. Step 2. Apply the kernel. Utilize the combined sum kernel within your Gaussian process regression GPR model. Using the kernel parameter metrics. Metric 1 mean squared error MSE. This commonly used metric assesses the average squared difference between the model's predictions and the actual values. Metric 2 root mean squared error RMSE. The square root of the MSE, providing a more easily interpretable measure of prediction error. Visualization plots. Visualization plot 1. Scatter plot of data with the fitted Gaussian process model. This plot helps visualize the model's ability to capture the underlying relationships in your data. Visualization plot 2. Heat map of the covariance matrix. This plot helps visualize the relationships between data points as defined by the combined kernel. Fine-tune parameters. Parameter 1. Parameters of individual kernels. Each kernel within the sum kernel will have its own set of parameters. Fine-tuning these parameters, e.g., length scale for the RBF kernel, is crucial for achieving optimal performance. Parameter 2. Hyperparameters of the Gaussian process model. The model itself has parameters that need to be tuned, such as the noise level, to find the best fit for your data. Uncertainty methods. Uncertainty method 1. Predictive variance. The sum kernel can be used to estimate the uncertainty of the model's predictions. This is represented by the variance of the predictive distribution. Uncertainty method 2. Confidence intervals. Based on the predictive variance, you can calculate confidence intervals around the model's predictions, providing a visual indication of the uncertainty. Challenges and fixes. Challenge 1. Overfitting the sum kernel. When used with too many kernels or inappropriate parameter settings, can overfit the training data, resulting in poor generalization to new data. Sample use case that resulted in challenge 1. Adding multiple kernels to model a complex dataset without careful consideration of the underlying data structure can lead to overfitting. Fixes to challenge 1. Reduce the number of kernels. Start with a smaller number of kernels and gradually increase complexity as needed. Use regularization techniques. Techniques like L1 L2 regularization can help penalize complex models and prevent overfitting. Perform cross-validation. Use cross-validation to evaluate the model's performance on unseen data and identify overfitting. Challenge 2. Computational complexity with many kernels. Calculating the covariance matrix can become computationally expensive, especially for large datasets. Sample use case that resulted in challenge 2. Modeling a dataset with millions of data points using a sum kernel with multiple complex kernels. Fixes to challenge 2. Optimize the kernel parameters. Carefully choose and tune the parameters of the individual kernels to minimize computational complexity. Use sparse approximations. Techniques like sparse Gaussian processes or inducing point methods can reduce the computational burden by working with a subset of the data. Consider alternative models. Explore other machine learning models that may be more computationally efficient, depending on your data and requirements. YAML. sklearn Gaussian process kernels. White kernel. Description: the white kernel, also known as a noise kernel, is a stationary kernel that represents purely independent noise. It is commonly used to model measurement noise or irreducible uncertainty in a Gaussian process GP model. The white kernel assumes that each data point is independent of all other data points. meaning there's no correlation between them. Inputs. X the input data. Typically a 2D array with each row representing a data point and each column representing a feature. Y the output data. A 1D array representing the target values corresponding to the input data points. Outputs. K the covariance matrix. A square matrix with dimensions equal to the number of data points. Each element key, J, represents the covariance between data points I and J. Coriag a 1D array containing the diagonal elements of the covariance matrix. These represent the variances of individual data points. Steps. Calculate the covariance between each pair of data points using the white kernel function. Construct the covariance matrix K based on the calculated covariances. Extract the diagonal elements of K to obtain the variances of individual data points. Metrics. Mean squared error MSE measures the average squared difference between the predicted values and the actual values. R squared indicates the proportion of variance in the target variable that is explained by K. Model. Visualization plots. Scatter plot visualizes the relationship between the input data and the output data, with the predicted values overlaid. Covariance matrix plot displays the covariance matrix K, highlighting the independence of data points. Fine-tune parameters. Noise level, a positive value that controls the magnitude of the noise variance. Increasing the noise level increases the level of randomness in the model. Uncertainty methods. Predictive variance, the diagonal elements of the predictive covariance matrix, which quantify the uncertainty in the predictions. Challenges and fixes. Challenge 1. Overfitting. If the noise level is set too low, the model may overfit to the training data, leading to poor generalization performance. Sample use case that resulted in challenge 1. A GP model with a white kernel and a low noise level is trained on a noisy dataset. The model fits the noise very well but fails to capture the underlying trend in the data. Fixes to challenge 1. Increase the noise level. This will make the model less sensitive to noise and improve its ability to generalize. Regularization. Use regularization techniques like L1 or L2 regularization to prevent overfitting. Challenge 2. Underfitting. If the noise level is set too high, the model may underfit the data, failing to capture any meaningful patterns. Sample use case that resulted in challenge 2. A GP model with a white kernel and a high noise level is trained on a dataset with a clear trend. The model fails to learn the trend, resulting in predictions that are essentially random. Fixes to challenge 2. Decrease the noise level. This will make the model more sensitive to patterns in the data. Use a different kernel. Consider using a different kernel, such as the RBF kernel, that is better suited for capturing trends in the data.